Hey guys, welcome back to another episode of Simuleo. So let's go ahead and get started with good news and bad news. Okay, so bad news first. There's a couple of bad news, there's a couple of good newses, so hopefully this will all even out. I'm starting late today, my apologies, it's 5:17 in the morning, and that is totally and completely my bad. For some reason, I have been sleeping in lately, and there's really little I can do about that. I really need to get better at getting up right at 5 o'clock for this stream, but hey, I'm sorry. You know, every once in a while it just happens. More bad news. I have, let's see, Thanksgiving. Hey, happy little rat. Thanksgiving is on Friday morning my time for the US. So because of time zones, even though it's on Thursday in the US, it is Friday morning my time. And I'm gonna have to cut that stream a little short, like literally only an hour, maybe an hour and 15 minutes, because I'm gonna have to Skype my family that day. Okay, other bad news. I guess I'll just kind of put all the bad news together. So the other thing is, there was some guy that I was trying to get to stream on Twitch for physics, and instead of choosing Twitch, he chose YouTube Live, which is fine, I suppose. In fact, in some sense, maybe YouTube is a better media for this kind of stuff, just because, you know, YouTube Live allows you to do a lot of stuff that you can't do on Twitch. You know, it allows you to backtrack on videos. You can watch the previous, you know, so if you're streaming for 4 hours, you can look at the previous 3.5 hours and some stuff like that while the stream is going live. That's quite useful. However, in my case, I think a lot of people watch my videos after they've been streamed. Maybe not a lot, but I know quite a few do. So, I don't know. I'm just throwing that out there that there was someone who changed to YouTube Live instead of Twitch. Now, the thing about this is, it's nearly impossible to find someone's YouTube channel, and it's pretty okay to find someone's Twitch channel. And at this point, the Twitch creative community is getting better and better, so I kind of feel like I don't have any reason to switch to YouTube Live, but I'm just letting you know that it did happen. Someone did switch to YouTube Live instead of Twitch, so that's a little unfortunate. It means it's going to be that much harder to make the Twitch physics community that I was hoping for, but hey, that's just how it goes. So, okay, now good news. Let's go ahead and CD into the appropriate directory. CD projects, Simuleos, and of course, genetic algorithms. Same thing over here, CD projects, Simuleos, and of course, genetic algorithms. And let me go ahead and cool this down. Type in Julia, and let's go ahead and include genetic.jl. Okay, so as of yesterday, we kind of ended on a bit of a sour note, so I wanted to point out that we are actually optimizing at this point in time. So let's see. Basically what we have here is a whole bunch of different time steps that I've allowed to pause every once in a while. So let me go here and let me go into vi genetic.jl, and let's go ahead and increase this pause from 0.5 seconds to let's do a second for each time step. Okay, so the first time step you're going to see is all of the random choices, right? So the idea with this graph, let's go ahead and pop over here, include genetic.jl. We have all the random choices, and then slowly but surely they all kind of converge to one, which is the minima of our function, right? So we had some discussions afterwards as to how genetic algorithm-y this genetic algorithm is, and this is fine. This is something that we can talk about later. But hey, Slayer Darth, point is we do have things minimizing on at 1. We have them converging at 1, which is the minima, and I'm happy with this for now. Now, going forward, we're going to be attacking a much more complicated system. This is kind of just a test, just to get our toes a little bit wet. And after this, what's with the fancy purple shirts? You're supposed to be majoring in physics, not fashion design? Oh, actually, I'll be honest. I have, I pretty much only wear collared shirts. And this is kind of because I have a bit of a, I don't like people looking down the back of my neck, so I always wear colored shirts because that keeps people from doing that. Outside of that, I find that colored shirts tend to stay better. Like, they tend to not break as frequently. So, like, I have some shirts, though none are in this room, but I have one shirt that I've had since I was 10, and I've worn it every single Christmas since I was 10, and I still wear it regularly. Like, I wear it at least once every other week or something like that. I really wish Twitch would stop kicking you from your streams when you have to log in. Oh yeah, that's fair enough, because then you have to watch an entirely new commercial and stuff like that. That's the one thing that really bothers me about Twitch, the commercials. I'll be honest, guys, those commercials are super long and annoying, and it's enough that I have considered switching to YouTube Live. I think if you're partnered with Twitch, you can choose not to show that commercial at the start, but I'm not sure. I have to ask on that one. So it is something that is a little bit of frustrating, but of course if you're using ad block, it's not that big of a deal. So I don't know, maybe it's okay. Yeah, so that's kind of why I wear always colored shirts too, because the colored shirts are, I don't know, they hold up better, and I've had them forever, and I actually have been wearing the same size shirt since I was like 10, because I was really, really big when I was 10. And then I steadily slimmed down at a rate such that the slimming down always allowed me to wear the same shirt size. So, yeah. That's kind of why I always wear colored shirts, because I have a whole bunch of them over the years, and they've always fit. And I always find that regular old t-shirts, which I do wear a t-shirt under the collared shirts, don't hold up. And yeah, it's pretty much that. Vampires, back of the neck, that type of thing. But yeah, so good news. This is optimizing around 1. I'm quite happy with that. I do think there should probably be lower partner requirements for creative streams. It's a different ballgame with different target audiences. Yeah, this is fine. I have not actually really desired at this point in time to become partnered with Twitch. It's not something that I think would help this stream out in very many ways at all. I might add emotes or something like that, and the emotes are okay. You know, so Beam is something I did hear about. So I've just now heard about Beam. Let me go over here and let's just go to, it's beam.pro. I heard about it just recently, and it does look quite nice. Don't get me wrong, it looks incredibly nice. So if we browse, we scroll down, they'll have miscellaneous down here, and we'd be streaming in the miscellaneous category. Yeah, you know, the thing is, less delay is fine, but I still feel like, you know, so if we go here to Mist, they have music. I don't know, we can go to like painting or something like this. They still don't have physics, you know? Like, it's not like there is a dedicated physics community. Oh, I'm sorry about that. It's not like there's a dedicated physics community. Now, if we go to YouTube Live, and we look for physics. Yeah, exactly that, Gustorn, and I totally agree. At this point, the discoverability on Twitch is the best, in my opinion. So if we're on YouTube Live right now, and we have YouTube Live Technology. This is where I would basically be streaming, because I'm a science and tech channel. If you look here, okay, what do we have? We have, well, this is all in Japanese. So nothing that I really want. So that's one problem. It's localized based on location, so it's kind of hard to find the streams that you want. Then if we scroll down, we don't really get anything where people are just talking until we go down here where people are doing, what do I call it? Google Hangouts, you know? And that's okay. Let me see. But there isn't really anything that's just, you know, like people talking. I mean, there is stuff down here, right? So this is just people talking, I guess. But it's all mixed up, and I don't know. I don't know if I really like that. It's just, it's hard to find what you want, I think. So, let's see. I've been on it. Being Microsoft, even if I have to use it for work. Yeah, fair enough. Okay, so the point is, I'm sticking with Twitch for now. I mean, unless there's some real big reason to switch, I think it's fine. Again, this stream doesn't need to be partnered. We get I set my bitrate arbitrarily low. And because I set the bitrate pretty low, it's not the biggest deal. So I think it's okay. So what do we have here? So this is now done. This genetic algorithm, for now, I'm just going to call this part of this code. Because we're going to have to come back and we're going to have to do something way, way more complicated in a little bit. But for now, today, because it's technically Thanksgiving in Japan for today, and technically I have a day off, that means I need to get to work early and I need to work really hard like every other day. So what I'm going to do is I'm going to spend today, and it might be a little bit short, but I'm going to spend today working on something else. It's a new system that we're going to apply genetic algorithms to, and I'm not really going to describe how we're going to use genetic algorithms yet. Instead, I'm going to just describe the system, and today, by the end of the day, I want to have a field generated and go from there. Yeah, so I've seen livecoding.tv too. But when livecoding.tv came out, let's just go ahead and pop this up over here. There was some really bizarre things that were going on with the live coding community. The person in charge of livecoding.tv basically went through, and there was this one particular female streamer who was streaming programming on Twitch, and or not Twitch, but streaming programming on livecoding.tv, and there was some weird things that that were going on there. So like, she said she wanted to close her account, and the CEO of livecoding.tv went and said, well, you can't close your account. And so she tried to close her account, and instead of closing her account, they actually defamed her account, and they said, don't watch this account, the lady has done this, this, and this, when she didn't. And so it was a really, I don't know, really bad situation where they actually they first of all couldn't just get rid of her account, and second of all, kind of, I don't know, they basically lied on her account as to why she was no longer streaming. So it was a little bit weird. Since then they fixed that issue. It was mainly a PR issue and stuff like that, but it was still kind of weird. Okay, I checked out live coding a few times, but it's odd. It looks like there are a lot of streams, but usually only a handful are actually live. The rest are previous recordings. Yeah, that's fine. Also, it doesn't appear to be much good content. Yeah, well, okay, but the truth is on Twitch too, right? I mean, if you're going to Twitch and you're looking for not programming content. Also, why is my screen still flickering? There's nothing I can do about this. It's just flickering. Again, guys, if your screen is flickering, just watch it on source. There's nothing you can do about that. Okay, hey Afaze, what's up? Okay. But if you're on Twitch and you're looking for, let's say, physics content, there isn't really anything else you can find about physics content, you know? Like, there's my channel, and then there's what? Nothing else, you know? So, arguing that there isn't very much good content out there, I just feel like live coding is a very small niche field at this point, and we need to grow it. You know, that's where we're at here. I found LCTV to be blah, but now they did their chat stuff. Oh, how they did their chat stuff, yeah. Okay, so let's go ahead and open up a terminal, and let's start talking about what a superfluid is and why it's interesting. And then we'll kind of do our field stuff. We'll kind of meander about a little bit today, and we'll get stuff done. Is this a white cat? I don't know. What does a white cat look like? 1 second. I have to pop up the chat. Simuleos. Oh, it's maybe. Okay. So let's do it. Wait, where's my pen? There it is. Found it. I'm not really watching for physics, to be fair. Though I'm watching for programming because I appreciate your communication style and the work you're doing. Fair enough. I started a new project and I think you're going to think it's pretty cool. All right, let me see what it is. What is it? Okay, so superfluids. Okay, so what are we doing with superfluids? Well, where should we start? First of all, how do we create a superfluid? So superfluids are hard to make, first of all. So don't go around thinking that you can just make a superfluid with a regular fluid. For the most part, you need an extreme environment to create a superfluid. The most extreme environments that I'm familiar with are incredibly cold atoms. So atoms at roughly 0 Kelvin. Now, okay, if you're using superfluid helium, it's easier to get superfluid, but there's another type of superfluid that you can create, and this superfluid is known as a Bose-Einstein condensate, or BEC. So Bose, 1 second, Einstein, 1 second, condensate. Okay, so what is a Bose-Einstein condensate? Let's just start with this, and then we'll describe how this all relates in a bit. Okay, Bose-Einstein condensate. Bosons. After superfluids, hyperfluids, and fermions. The difference between these two types of creatures, they're both atomic creatures. This guy has even spin, and this guy has odd spin. Okay, now what does this actually mean? Well, let's go to new page before. If we plot the wave function of a boson, it is symmetric. If we plot the wave function of a fermion, it is antisymmetric. So this is boson, this is fermion. And for this reason, as we cool the particles down, so as we cool, on the next page. Let's put them both in harmonic traps. The fermion does something a little bit weird. Because the wave function is antisymmetric, these guys always pair up. So you always have an upspin and a downspin, an upspin and a downspin, an upspin and a downspin. Simulos, it has kind of evolved as I've been thinking of what I want, but it's going to be a modular bot system that has Twitch access. It is coded in Bash and uses the IIRC client to access the chat. Right now I've got it set up so it has OBS integration, uses XDoTool plus OBS keyboard shortcuts to control the layers that are shown in OBS. Oh, neat. More like coming up after Superfluid, relaxing with some high quality H2O. It does this by cracking the which program I've got active and shows that. Huh, super interesting. I'm interested to see how it works. I might pop in to take a look at the bot soon. Okay, so like we were saying, fermions over here, they pair up, and everyone's familiar with this. This is the Pauli exclusion principle. Now, here's where things get principle. Okay, here's where things get a little bit weird. Bosons, on the other hand, because they're symmetric, don't really have this up and down spin. Instead, what happens as they cool down to absolute zero, all of the bosons exhibit the same macroscopic state. They're all in the same state. And this is absolutely crazy, because this means that we see some weird emergent properties. And I call them emergent properties, but if you guys actually know the jargon here, they aren't really emergent properties here. But here, let's just describe what actually happens. So we have a Schrodinger equation, which is d over dt psi, maybe I shouldn't have started with this, d over dx squared, let me see. Let's actually just make this a del squared. Plus v, okay, something like this, psi. Okay, we have some sort of momentum component, I think this is over 2m, whatever, h bar, something like this. Okay, there we go. We have our momentum component, our potential component, and stuff like this to our typical Hamiltonian. So before, if you're not familiar with what this is, basically we have a trap. That is our v term over here. And this term is the momentum term, so it's related to, like, I suppose, the movement of all the particles, the wave function that we're working with here. Now, in a BEC, we add an additional term, g psi squared, which is due to the interaction between the particles. Now, what's crazy about this is if we solve the Schrodinger equation, we get fundamentally different dynamics than when we solve the Gross-Pdevsky equation, or solve this new equation we have for the BEC. Anyway, one of the new things we see is that the BEC is superfluid. This is kind of where you'd expect to find a superfluid, in a laboratory somewhere off in the distance. You know, you don't usually see it in very many places. You'll see it in like neutron stars and things like this too, but this isn't something that you would expect to see in everyday life, and I had to point that out. What I think I'm going to be coding, I'm taking a break from the OS stuff to do this because it will allow me to show off what I do. Fair enough. It's going to use tmux to create command line frames, besides graphical frames on top within Twitch OBS. I'm going to deal with emotes, though having the bot track chat when people run emotes, it will temporarily show ASCII versions from the terminal. Good luck with that one. I feel like it's going to be quite difficult. Okay. So, now what exactly is cool about a superfluid? Well, let's say we rotate a normal fluid, and for this, I'm just going to do a Google image search, because you guys are going to hate this. Let's Google image search vortex, okay? So if we, images, okay, here it is, water vortex will work. Okay, so if we rotate a classical fluid, visit page, we get a vortex. And these vortices come from many different places, right? So we have vortex that looks like this, like that. Everyone is familiar with what a vortex looks like. It is simply a rotation along any axis, and we get, of course, something that looks like this. It's a spinny thing that looks like that. Now, in a superfluid, things work a little bit differently. And in a superfluid, what ends up happening is rather than generating one rather large vortex, we generate many smaller vortices. And this is where things get a little bit weird. I've already got the framework for most of the setup. I just not stuck it in the bot yet. I see, fair enough. So what I do for research is I actually study these superfluid vortices. And the superfluid vortices look absolutely bizarre. So let me pop over here. Let me do a quick WQ, a quick D, and CD back a couple directories into the directory I use for research. It's fine, it's open source, so I can't imagine my boss is going to have any problems with this. And if he does, oh well, I'll take the stream down. It's fine, it's like 10 people watching. Okay, so what do we do here? Let me go into CD Pi, and I create a very stupid plotting script here. So let me do a quick ls of which data I actually have available. Looks like I have a whole bunch of data available. So let me just plot something at random. So I'm going to do Python plot item wave function range. Let's do 0, 5,000, 5,000, something like this. Okay, so we're going to plot it. And what we do is if we start with an initial wave function, which is just some sort of Gaussian that we said, okay, this is where all the particles are starting at. And then we rotate and cool it. Eventually, it forms. Hopefully, this is going to form what I want. Oh, 1 second. Maybe not. Let's try a little bit longer. Let's try 45 to 50,000. Okay. Eventually, it forms. Oh. Oops. What did I do? Starts at 45,000. Goes to 50,000. And steps to 5,000. That's what I wanted. 1 second. Give it a second. Okay, it forms a whole bunch of smaller vortices that kind of pierce the center. Okay? So basically, we went from that initial Gaussian that you saw before to something that looks like this, where basically it is a plane with a whole bunch of circles piercing the top. I've actually already got the framework for it, mostly set up. I've just not stuck it in the bot yet. Okay, so, and obviously these vortices are, in a way, topological defects, I suppose you could say. But yeah, they're basically just holes piercing the Bose-Einstein condensate. And it's quite interesting, you know, what you can actually do with these vortices. So, now, what are we going to do with this? Well, right now, I just want to calculate the field created from the vortex. And here's where things get absolutely bizarre. So, a vortex is directly related, or rather, the formulas for a vortex look exactly like the formulas for a magnetic field around a wire. Round a wire. Now this is absolutely bizarre. It's crazy that this happens. But, new page before. If you've ever taken a freshman physics course, you'll know about the Biot-Savart law. Okay, now I don't know if I'm pronouncing it right. Don't get me wrong here. I have no idea if I'm pronouncing it right. But this guy right here basically is a way in which you can probe the magnetic field on the outside of a wire. Now, what we're going to do is we're actually going to derive the magnetic field outside of a straight wire using Maxwell's equations. And then we're going to describe how this is changed for a vortex. So let's pretend we have a wire right here. If we have an electric field going through the wire, some sort of current I, right? And we have some sort this means that we have some sort of magnetic field going through the wire like this. So it's wrapping around the wire in this direction with a field strength proportional to mu naught I over 2 pi, and then your distance from the wire s. This is actually relatively easy to derive from Maxwell's equation. So if we deal cross B equals mu naught I plus other terms that we're going to be ignoring from now. Basically, all we have to do is an integration over here. Let's see, of del cross B equals mu naught I. Same integration over here. And basically what ends up happening is over here we get, we integrate via a circle, right? So this goes from 0 to, let's say, 2 pi. And this guy goes from, I don't know, 0 to s. And what ends up happening is we get mu naught I over 2 pi s. I'm not going to bore you with the math here. I'm sure that a lot of people have done it. I'm just mentioning that we can go from Maxwell's equations to here, okay? And so with this, we now have a formula for the magnetic field on the outside of a wire. And now what we can do is if we assume that we have a vortex going through. Hey, Kark, thanks for coming in. I guess you're leaving. Appreciate it. So if this is a vortex instead of a wire, I gotta lurk and give my mom some opinions on furniture and such. I'll definitely like to talk to you sometime when you're not busy about the bot stuff. But yeah, that's fair enough. Yeah, I'll definitely keep in touch because it seems super interesting. So if this is a vortex instead of a let me see, not equal to wire, it ends up being that the velocity is equal to some sort of circulation over 2 pi r. And this is absolutely crazy because this means that Well, it means a couple of things. First of all, the circulation around every vortex is quantized, which means that in a superfluid, if you rotate super fast, it ends up being that we have some sort of, let's look at it from the top, here's our vortex, phase that goes around this way, where it starts at 0 here and ends at 2 pi. This is crazy, because, for a number of reasons, okay? So because these guys follow the same formulas as wires, page new, page before, you can imagine that vortices, like wires, current carrying wires, must somehow connect with some sort of sink or source. So like, for example, with a wire, you know, you wouldn't expect a wire that is carrying current to just dangle an end in the middle of our fluid, right? So let's say we have something that looks like this, and we have some sort of electric charge here. Well, there's no way it's going to be entering this system unless there's some sort of sink, right? Because the yeah, we'll see what happens. I'm definitely interested in it, so we'll see what happens with the bot thing. So let me see. In order for current to be carrying through the wire has to have some start and end location. It's the same with a vortex. A vortex in a superfluid must either end with itself or end at the edge of the superfluid. And this is super duper interesting, because this means that there's a whole bunch of equations that we can use to probe the field on the outside of a wire and go from there. So today what I want to do is basically write a very short script to get the field kind of set up and then go from there, you know? I'm interested in kind of seeing the best way to split up the magnetic field and stuff like this, or the velocity distribution, such that we can better approximate basically where the superfluid vortex is. And we'll be using the genetic algorithm to first probe where the vortex is, and then later for reconnection events. But reconnection events are a little bit complicated, so I wanted to start with the field, move on to the vortex identification, and then go on to the reconnection events after that. It's all kind of interesting, and this is actually I don't know, I think this is going to be really interesting for you guys, but maybe not. Maybe you guys are only really interested in the in programming, which is fair enough, because I'm in the programming category on Twitch mainly. So if this is not interesting to you, I totally get that. But you know, this is super interesting for me at least. So we'll see how this goes. Okay. So now, 45 minutes in, let me go ahead and get a quick sip of water, and then we will go from there. So let me do a quick clear here, and let's cd into, I don't know, projects. 1 second, cd layouts. And let's do another guy here, cd projects. 1 second, projects, cd layouts. Okay, let me get some water. Okay, so I think I finally started realizing what gets you guys interested in stuff, though. So the sources and sinks for vortices are either the edge of the condensate or another vortex. In this way, let me just go ahead and look up superfluid turbulence. 1 second, turbulence here. Okay, images is what I wanted. We get some sort of super complicated vortex tangle. That's okay, but that's not what I'm looking for here. I'm looking for maybe something like this. Oh, that's hard to see. Oh gosh, these weren't the images I was looking for. In normal fluid, they are different in state, at least. Yeah, so in this case, the vortex must either end at the edge of the condensate, like the edge of the superfluid, or reconnect with itself in the form of a vortex ring. This is the only way you can do it. So if we look at a picture of this guy, I guess do visit image, scroll in, all of these lines, they either end at the edge of the condensate, or they reconnect with themselves. Even though it's a super complicated vortex tangle, I can promise you that's what they do. So the sources and sink end up being like, you know, we could have a current carrying wire that's in a circle. We could have it end at the edge of the condensate, something like this, but has to end somewhere. And it has to end outside of the superfluid. So it's actually a super simple system in the end because of that. Okay, so I'm going to go over here and I'm going to make a new directory. And I'm going to call it Superfluid. Okay, and now we're going to cd into Superfluid. And we're going to do the same thing over here. Make directory. Oh, actually, cd Superfluid, since it's already created. In normal water, vortex in a kitchen sink would be from the surface to the drain. Yeah, this is true too. So the superfluid vortices are, how do I put this? In a way, a superfluid is a fluid without viscosity, right? So viscosity is a drag force you naturally have in your fluids. So let's say honey has a very high viscosity when compared to water, which has a much lower viscosity, but they're still super viscous when compared to air, which has a much lower viscosity. A superfluid has no viscosity at all. So this means that there is no drag in the superfluid. And this creates a whole bunch of weird things. Okay, so let's go ahead and open up a new file. I'm going to be using Julia again for this because we did our genetic algorithm in Julia, and all of this is related in ways that we'll describe later. So let's go ahead and open up, let's do, I'm going to call it vortex.jl. And for now, we're just going to open, basically create a very simple vortex distribution, something that has, you know, basically a field, and that's basically it. I just want to calculate a very simple field and go from there. So what I'm going to do then, I want to do the following. Let's go ahead and do vortex, one second, .jl. Let's keep going from here. And, okay, so the purpose here is to find a field on the outside of a superfluid vortex. 1 second, X, okay? Wait, what am I doing? Oh my gosh. I'm doing very bad at this. 1 second. Okay, so now we'll keep going from here. Now again, if you're unfamiliar with Julia, there's a whole bunch of little things here and there that we'll end up using. For now, let's go ahead and create a new type. Types are kind of like structs or something in C++. And we're going to call this type vortex. Oh, field. I'm sorry. Okay, and let's go ahead and end the type down here. And in this type, we need a couple different guys. So let me see here. We can, I suppose, keep a couple of ints. So let's do resolution. The vortex forms is intended to stabilize the difference. Yeah, that's fair enough. Okay, so what are we going to do? Let's go ahead and create a whole bunch of different characters in this type field. So let me go ahead and open up Julia over here, just to make sure I'm not doing anything syntactically funny. And what we're going to do is we're going to say x. Let's see, what do we have here? We're going to have a vector for x, y, and z in here. So let's do x, which is a vector. And let's go up here and let's go ahead and write down x dimension, which is going to be a vector. Oh no, this is just going to be an int, 64. And the same for y and z. So let's go ahead and do ry and rz. Okay, now we have x, which is going to be a vector. Oh, 1 second, vector. And this vector is going to be of size x dimension times y dimension times z dimension. It's going to be, yeah, it's going to be a size grid size. So let me see, how do we initialize that again? I think it's like super weird in Julia. But let me just go ahead and put it in a comment. So this is going to be a vector of, and let's say doubles, I suppose. So it's going to be float 64. And we're going to do the same thing for y and z. So ry and rz. Okay. And let's go ahead and put up here and say x. How do I do this? X, y, and z are all of size. Let's do x times, or x dim times y dim times z dim. Okay, so this is going to be our size, basically. And in the end, we'll have some sort of weird index and stuff like that. But let me just go ahead and put this into Julia just to make sure it does compile, so I'm not doing something really stupid here. Yep, seems to compile just fine. So now we're going to say a is going to be equal to field here. And then a dot x, let's do x dim equals 10. No field x dim. Macro expansion. I just set a equals field. 1 second, I gotta think here. Type, data type has no field x dim. Oh, maybe because I need to do the following. Let me see, error, no message matching field. 1 second. Maybe do field of A? Nope, okay, 1 second, I gotta figure this one out. Okay, so now we probably need initialization or something. So how do we do initialization of types in Julia? Let's go over here and let's do it. Initialization of types, Julia. Okay, let's do it. Constructors. Sure, that'll work. Types. I think this will work just as well. Types. Let me see. Int. I want. Oh wait, nope. These are all different types. Dagnabbit. Components types. Immutable. complex, real. In the end, immutables will be faster than other types. Let me see, parametric types, parametric composite types. 1 second. Let's do initialization constructors. Hopefully this will be it. So we say foo12. Oh. Well, that's, outer constructor methods. So I guess if we wanted to do this, I'd have to do something like field of, let's say, 10, 10, 10, 1 second, 10. And then we would want fill. Let's do 0.010. Fill 0.010. And then fill 0.010. Invalid numeric constant 0.0. 1 second. Fill 0.010. Okay, so that seems to work. Invalid numeric constant 0.0. What's your deal with that guy? It seems to work just fine. What if we just do 1 second? 10, 10, 10, 10, 10, 10. This is not going to work. Yeah, okay, let's create a new guy. So let's just create a simple type and let's go from there. My apologies, guys. I was not expecting to run into issues because I've done many types before Julia, but I kind of forgot the syntax. So that's okay. That's how it goes sometimes. So we're going to say type check. And in here, we're going to say x. And it's going to be an int 64. Array, not a vector. Array is basically a vector. They're basically the same thing. Let's go ahead and end there. Now let's say a is going to be equal to check. This is going to be equal to 5. Okay, so now if we say a dot x. Dang, that worked. Okay, so let's see, vector float 64. What is our dealio here? Fill each of these guys a vector. So what if we just say b is going to be equal to a vector. Let's say vector float 64. And this is going to be equal to fill 0.010. Syntax. What the heck? Deprecated syntax. Instead use global b. Type assert b not defined. What the heck, guys? Let's go over here. B is equal to this. Of course this is going to work because, dag nabbit. What microphone am I using? I'm using a SM58, let me see, Shure microphone. And I'm also using a Focusrite, let's see, Focusrite Scarlett Solo, whatever it's called, preamp, that's what I'm looking for. Then I'm over here and I'm using let me see, calf jack host to put a compressor on it. And then that's basically what I've got. So, I'm using it in Linux, so I can't guarantee you have the exact same situation that I will. Okay, so fill 0.010. It is a 10 element array, float 64 1. That's what I wanted. It's a vector float 64. So this is what's kind of getting me. So let's say that. Okay, let's just do array float 64 1. Why not? Let's see if that fixes it. Maybe it will, maybe it won't. Who knows? Let's go up here. Let's put down array float 64. Oh, here, and now let's add in a comma 1. There. Okay. Okay, so now let's see what happens if we grab this, put it over here. No method definition array float array 64.1 in module main overwritten at REPL method definition. Let's just control D, Julia, pop it down. There we go. That one seemed to work. Now we're going to say B is going to be equal to fill 0.010. There we go. And we'll say A is going to be equal to field. Let's see. What do we want here? Field of 111 B. Okay, this one seems to work. That's okay. Yeah, I know. That's what I thought. They're literally the same thing, but this one works. The other one doesn't. Don't know why. That's okay. Okay. So now what we need is a function to initialize everything. So let's go ahead and pop down here. We're just going to say function to initialize our field. And in here, we're going to say function init, and it's going to be xdim, and this is going to be an int64, ydim, and this is also going to be an int64. 1 second. This is going to be int64. This is going to be zdim, int64. Okay, so that should be all we need for the start here. Let's go ahead and end that. And let's see, what do we do from here? So all we have to do is initialize everything. So what we're going to say is the following. Since x, y, and z are all going to be of size, wait a minute. Float 64 and 1. Yeah, okay, that's fine. 1 column. And float 64 all along that column, I suppose is what that's saying. So let's go ahead and do this, and we're going to say empty array is going to be equal to the following. It will be fill of 0.0, and we're going to say xdim times ydim times zdim. So let's go here and let's say gsize. Gsize is going to be equal to xdim times ydim times zdim. Because they're all ints, I don't think we need to specify the type. And then we're going to say this is going to be f size, g size. Okay. Now what we need to do is we need to put this guy into our initialization function. So we're going to say return, let's say field of the following. So we're going to say xdim, ydim, and we do zdim. And of course we do empty array 3 times. Let's grab this. Let me see. We'll just grab this guy. Good. A. Then we do empty array. Empty array. Okay. Gosh darn it, I just can't type at all. Just period. My typing is just bad. Here's our initialization. It's not very difficult. I just figured I'd put it into a function because, you know, it's fine. It's just a little bit simpler. Okay. So what are we going to do now? So now what we need is we need a function here to find the field around a wire. So this shouldn't be so bad, right? So we're going to have an x, y, and z fields. And I suppose what we can do, I suppose we can actually put the type field into another type a little bit later. But for now, let's just go ahead and find our velocity field around a single vortex line. And then we'll kind of go from there. So in the end, we're going to be using this field for a number of different things. So we want to just make sure that we can appropriately find the velocity around this 1 second, around this vortex, and then we can go from there. So let me go ahead and put another comment up here and say field type will be used for velocity field around vortex. Okay, so now what do we have to do here? I guess we can call this function whatever we want. So let's go ahead and say this is a function to find velocity around vortex. Now here's where things get a little bit interesting. I haven't decided exactly what shape I want for our vortex. So for now, I suppose we can just do 2-dimensional vortices. And after doing a 2-dimensional vortex, let's just see if we can generate the appropriate vortex distribution around a single vortex in the center of our, let's say, condensate or something like this. So let's do that. So we're going to say around a vortex in 2 dimensions. Okay, so what we can do then is I suppose we can create a whole bunch of vortices at a particular location. So let me go up here and let's go ahead and create a new type, which is type position. And here's, I suppose, where... No, this should be okay. This is fine. We need xdim, ydim, and zdim. This is good. So let's go here and let's do type. Let's say field. Oh, I'm sorry. Position type. Position type will be used to find the location of vortices. This should be okay. So now we're going to say type position. And in this type, all we're going to do is put in x, y, and z. So it's going to be x. I guess this is okay. Int 64. Then what do we do? I guess I paste ry rz. Okay. So now we have the type position. Let's go ahead and do this. And what do we want? I suppose Vortex 2D is what we call this function. So let's do function, and let's call it Vortex 2D. Okay. What do we need in here? I'm not really quite sure, so I suppose we need a position of a vortex. And this could be a vector of positions, I suppose, and that would be okay. Julia types begin with capital letter. Okay, that's fair enough. I can go and change that. Let's go here. That's a P. And this is a P. This is Julia. That's the programming language we're using, RP. Dane de World, thanks for coming in. So the programming language that we're using is kind of a newer language, but it's good for fast things. It writes like Python, but it runs faster than Python typically does. It's not as fast as C, although they claim you can get it down to C speeds. So that's something that I'm interested in working or trying to figure out. Again, my roommate gave me a whole bunch of interesting optimization tips, but they weren't really anything I didn't already know. It's just kind of, he gave me some ideas to speed it up even faster. So for example, changing types to immutables would be rather quick. But let's kind of not do that for now, and let's just kind of leave types, and then we'll change them to immutables. We'll see what kind of optimizations we can do at the end. So what do I want here? I suppose I want a, yeah, I suppose I want a Vortex 2D, and in here I'm going to say Vortex location. So let's say location. And what do I want here? I suppose I want, how about we call this find field 2D? Something like this. And then in here we just give it a vortex location. So let's say location, and this can be a vector of positions. Okay, something like this. And let's go ahead and end that. That was not how you spell end. There we go there. Okay. So all we need to do is we read in this vector of locations, and then we just kind of update the field at every given point. So like I said before, the field is going to be some sort of gamma over 2 pi r. So basically, as long as we have something over 2 pi r, because gamma is a constant, we should be good here. So then after this, all we have to do is kind of plot it, and I guess we'll do the plotting in pyplot or something like that. I haven't quite decided how best to do the plotting. I'm most comfortable with like nuplot or something, but we'll see. Sorry, I need a little bit of water. Okay. So like I said today, if we finish early, we finish early. I'm not particularly worried about that today. So what are we going to do? So first of all, we need some sort of loop that goes through all of the different dimensions, right? So let's go ahead and initialize our field here. So we're going to say, let's see, what do we want here? Up here, we should probably read in an X dimension and a Y dimension. Good. So now what we're going to do is we're going to go ahead and initialize our the field. So we're going to go here and we're going to say init. Let's say velocity is going to be equal to, and I guess it's going to be init, and I suppose this should be init field, just be more init field. Sure, it should be, I don't know, I'll figure it out. Okay, so let's do xdim, ydim, and then 0. So it's going to be xdim, ydim, and then 0. Okay? Now, what do we do from here? Is that 3 spaces instead of 4? Dagnabbit. Okay, so now we have 4 spaces. That should be okay. Velocity is init field. And what I might want to do is I might want to split this up into a vel x and a vel y. Just for now. We will we'll comment on this later. We have better ways of doing this, but for now this will be okay. So now we have our vel x and our vel y. It's going through y dimension and x dimension. Okay. And what we're also going to have to do is we're going to have to plot some stuff in the end. So we'll figure out how this goes too. Let's go ahead and get started though. So we're going to say 4, and because it's 2 dimension, we're going to have to say I equals 1 to x dimension. And then we're also going to need another loop in here. So let's go ahead and end that. And we're going to say, 1 second, 4, looks like Julia file. It is, looks like Julia file. What do you mean? This is Julia programming? Definitely. So let's do 4, j equals 1 to y dimension. And let's go ahead and end that in here. Okay, so now in here we're going to have to create an index. Let's go up here and let's do Sheldon or Leonard. I don't know, because I don't know either of them, but I am a theoretical physicist. So I think Sheldon is a theoretical physicist, so I think I'm closer to Sheldon. But again, I don't watch Big Bang Theory, so I'm not really sure what the difference is there. My apologies for that. Okay, so what are we going to do here? Let me go ahead and also create an index, and the index is for, let's say, internal keeping of the indices, or something like this, because we're kind of saving a two-dimensional file or a two-dimensional object in one-dimensional. We need a separate index, so we're gonna call the index, and it's gonna be an int 64. Oh wait, you can't do that here. We're just gonna say index is gonna be equal to 0. Ooh, okay, that was what I meant to do. Index, and let me go over here just to make sure we can do this. Index of int 64 is equal to 0. Yeah, okay, so let's not call it global. Let's just set it equal to 0. And let's do that. Okay, so now we're gonna go up here and we're gonna say int index is going to be equal to the following. Now here's where things get a little bit weird. Because we're doing this indexing here, we get to actually choose how we do our indexing. Now, we can do this in a number of different ways. What I typically like to do is make sure that the data is coalesced, which basically means that we're accessing nearby elements as often as possible. So this means that we want j to be our primary index, so that means we're popping down y first, and then we want plus I times j x dimension, or y dimension, sorry about that. And let me just go ahead and explain how this is working, because sometimes this indexing can be a little bit funny, and to be fair, we can use like a vector inside of a vector or something like that. But just to explain what the indexing that we're doing is, I kind of feel this is a little bit important. So we have our grid here, right? And we can do whatever dimensions we want. So let's just kind of do this here and this here, okay? So this down here is going to be our y, and this up here is going to be our x. Those are the worst squirrely brackets ever created. Anyway, here's the idea. We're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? Where it's basically going to be j counting in the y dimension, right? So we always do 1, 2, 3, 4, 5 down here. And then it's going to be plus, so it should be j plus, and then it's going to be I times y dimension up here. Where basically it's going to be, let's say we're at 1, so this means j is going to be equal to 1, right? So j is equal to 1. Y dimension is equal to, in this case, 5. So 1 plus 5 equals 6. And it goes on further. So let's do 11, 12. It is raining outside. 13, 14, 15. So this means, okay, we have 5 down here. So j is going to be equal to 1 again. We reset the I loop. It goes up to 10. So I is going to be equal to 2 times y dimension. So that's 10. We get to 11. Does this kind of make sense, guys? So we're doing the indexing in this way. So it's kind of a one-dimensional, it's 2 dimensions, but it's squished down to 1 dimension. Reason we're doing this is for a number of different reasons. Like, in my case, I need a one-dimensional array to put it onto the GPU for a whole bunch of different stuff. And in the end, we may or may not do GPU stuff with Julia here, because there is the Julia GPU stuff. And quite frankly, it looks quite nice. To the point that it allows us to do all the GPU computing we want, just with a little bit easier than CUDA. So, I don't know, I thought maybe at some point we might pop into that too. I do, for work, always use GPU computing for all my stuff, and it's super fast. In fact, we're getting some new trinkets. I'm super excited for those new trinkets coming in. But point is, super fast. Hopefully, this all works out. So, let me go ahead and pop over here. That's kind of what we're doing here for the index. I hope that makes sense. And again, guys, if you have any questions, comments, concerns, please let me know, because I am totally interested in answering those as soon as I see them in chat. Now, of course here, guys, we only have an x dimension and a y dimension, and I just realized I screwed up the field here, I think. 1 second. So we have xdim, ydim, and zdim for the field. There's a reason to use Julia. I've heard that Python and MATLAB are pretty popular choices. Yes, so the reason I'm using Julia is because, first of all, it's a newer language. The I should start at 0. No, it's fine if it starts. Oh, it should start at 0. You're totally right. So it should be xdim minus 1. Yep, you're good. Okay, I'm used to C syntax. Everything starts at 0 in C syntax. Okay, so the reason I'm using Julia is just because basically I'm kind of familiar with Julia by now, and also, I don't know, I'm a little bit active, or at least I know the Julia development community quite well, so... Oh no, so no one really uses Julia yet, because it's a new language, but The hope is that Julia replaces Fortran. Will it replace Fortran? I don't think so, but it'd be nice if it did. You know, that'd be cool. Fortran is one of those languages that's been around for a very long time, and could definitely be upgraded. That said, it is still currently as fast as you're gonna get for physics problems. So unless Julia can, you know, beat that speed, people are still going to be using Fortran for a number of different reasons. Okay, so let me see. Field is gonna have an X, a Y, and a Z. And so for this reason, I don't really like how NumPy code looks. Yeah, I can see that. For this reason, I just realized I screwed up. We don't need a vel X. We already have vel X in there. Okay, so now what do we do? Fortran. I've heard so many things about it. It's like Unix, old and never really dies. I mean, I used Linux and Unix pretty much exclusively. Supercomputers always use a Unix-based system. I mean, they're always running Linux, you know? So, I mean, there are definitely places. MATLAB is a lot slower, but it has a lot of built-in functions and tools. Yeah, that's true. By the way, Frankie for Chess, thanks for coming in. Let me see. MATLAB is a lot slower, but yeah. Like HP, AX, Oracle, Solaris is still deploying. It's still, yeah, of course they are. Yeah, like, I'm confused. Okay, so, let me see. Okay, so I work on large clusters, right? This is what I kind of work on. Granted, I really only use GPU nodes in the large clusters, but I do a lot of stuff with these clusters. I'm quite familiar with them. And I'll be honest, it's a completely different world than the world that most people live in. So though desktop computing is at a certain stage in a certain universe, supercomputing is at another stage in another universe. And it's just, they're two completely different objects that you can't really relate to each other. And so when people kind of look and they're like, wow, what is Linux used for? They don't realize 99% of supercomputers use Linux. I made that up. It's not 99, but it's super high. Like, pretty much all of the top supercomputers use Linux. There's like one that's using some sort of Unix-based variant, but for the most part, it's all pretty much Linux, you know? And this is kind of the thing, right? If you work in computational physics, where you are actually using these clusters quite regularly, you'll run into situations where all of these weird kind of legacy code type of things pop up. And that's because they're still useful for a number of different reasons. So, yeah, this is true too. Totally true. Because Linux is just, it's easier to use, you know? 99% of computer objects. That could be true. I don't know the stats there. But you guys are both probably right. Okay, anyway, we have our indices. So let's go down here and let's go ahead and find our velocity here. So what do we have? Well, after we go through all the x and y dimensions, let me see. We also need to basically add the field for all of the different vortices. So we have all these vortices. So what we're going to do is we're going to say 4. And this is where you get, okay, we could maybe do this faster. 4k equals 1 to, let's say, where are we? Length of positions, locations. So now we're going to add up all the vortices, and we're going to end here. So we have our index. We're going to end here. And let me just put in a quick comment here. So now we're going through all vortex locations to find magnetic or velocity field. Okay. Windows winning in desktop while Apple eat it profits. BSD is also a player, but really depends on your use. Yeah, I suppose so. Let me see. How much R or MATLAB do you or other theoretical physicists use? Okay, so to be fair, R is used a lot, but not by physicists. It's used mainly by biologists, from what I see. Now, maybe when people go into particle physics, when they have a lot of data and they need to do the statistics and stuff, they might use R. I don't know. I have never been in a situation where someone has chosen to use R over some other variant. Now, I know in astrophysics, people use a lot of Python. Now, MATLAB is one of those things that I had never really seen used until I came to OIST, and now my entire lab basically uses MATLAB. So it's kind of, it depends on where you go. But for the most part, if you're doing computational physics, you're going to be running into either Fortran, C, CUDA, or languages like this, super fast languages that are down to the metal. If you're doing theoretical physics, you're going to be seeing MATLAB, Mathematica, Python, languages that are easier to use, but still allow you to get something done. So Mathematica is one of those big languages that people like a lot. If you're doing a lot of data analysis, that's where you're going to want to use R. This is kind of what I currently see. So yeah, MATLAB's used a bit for theoretical physics, but it's not used maybe as much as you might expect. Let me see. I tried BSD once, but no one distributes BSD binaries. Fair enough. Let me see. Move to B and C some user. Replace Arch. Thanks to being binary of the source. I like BSD much more than Linux kernel. Back when I bothered to waste time with Linux. Waste time with Linux. For the record, Linux and Unix. So, for example, theoretical physicists typically always use some sort of Mac or Unix-based system, right? They usually use Linux, or they usually use Mac or something, because they always have to interface with clusters, right? And it's just a pain to have to interface with clusters when you're doing Windows. It's okay, you know. It's not like it's impossible. It's just it could be easier, you know. And with Windows or with Linux and Mac, you immediately have access to a Unix terminal, and that's nice. It's nice. And also, yeah, I'm also using Arch Linux. Sorry. So we're gonna go through all the location, all these guys' location. Okay, so let's pop down here. Yeah, that's I think basically what people end up doing. I could be bothered with Arch crashing. It always comes down to kernel updates. Even Fedora crashed for me because of kernel update and Skylake box. What is a Skylake box? And yeah, Putty is the most used SSH guy to go on to clusters. Man, I'm just talking too much today. Okay, let's go from here. It's a long-term stable kernel that I want for my workstations. 1 second. Sorry, I had to fix something that fell down. Okay. Okay, so we have all these guys. Now all we have to do is basically probe their velocities. So let's go over here and let's go ahead and describe what exactly we're doing. So new page before. In a circle, we have a couple of different guys that we have to take into account. So let's draw a circle. Okay, now what we've done here is something maybe we shouldn't have done, but we did anyway. So you guys are gonna have to deal with it. I split up the velocity into X, Y, and Z. Okay, so if we want to basically put this in appropriate coordinates, so we have X, Y, and Z, right? I've been running the same Arch setup for 4 years and had one update that temporarily killed my system. Yeah, probably update after they removed the move to System D. The move to System D was a little bit complicated for me. I will totally admit that one took me about 30 minutes to fix. But everything else, I haven't had any problems with Arch, you know? There was one time, and that was the System D update, but everything else is fine. Okay, so let's say we have something in the theta direction. That's the direction kind of moving here, okay? So the theta direction, let's see. I like Arch, but their switch to System D really changed what Arch stood for. Yeah, so you're one of the old school Archers. That's fine. I totally admit I was also one of those people who really liked the rc.conf file, and it was super easy. But when they switched to System D, I gotta admit, System D is nice. You know, I didn't like System D because it was something that I didn't know. You know, but now that I use it a bit, it's like fine. Okay, it's not quite as usable as the rc.conf file, but it's good in its own right. You know, I don't mind it. Okay, so what we need to do is we need to split this guy into an X and a Y. And a Y. Okay, so we have something in the theta direction, and we need to put it into an X and Y. So let's see, what do we have here? Well, we know that r cosine theta is going to be equal to X. That is going to be this line down here. And r sine theta is going to be equal to y, okay? So this is how we're going to split it up into x and y, and we'll basically have a velocity distribution in x and y. Arch used to be the Unix of Linux. Simple, clean, fast. It's still simple, clean, and fast. I would argue that it's still pretty good. Okay, so in this case then, what do we have? We have a theta, which means we have some sort of movement in this direction. So what are we going to say then? If theta is equal to... Oh, I'm sorry. It's in the theta direction, right? So if theta is equal to 0, then we have everything in the x direction. Yep, so everything's going to be in this direction. And we have theta equal to 90, or pi over 2, is all going to be in this direction, right? So in this way, we can kind of sort of see what we're getting at here. And basically, all we have to do is keep track of the angle that we're at from the individual location and go from there. So first of all, we have to find the position, and then we have to find the difference between our position and the position that we're at, find the angle, and then we're good to go from there. So I guess we're just going to do it. No problems there. Okay. So let's pop over here and let's do it. So first of all, we have all these different locations. We're gonna have to first find the distance and angle to the vortex center. Okay, so let's do that. What are we gonna do then? I guess the main thing we need. Okay, we do need distance. Definitely need distance. And we also definitely need angle, so we need both of them. So let's go ahead and say distance is going to be equal to the square root of the following. So what do we have here? We have the index there. And now here's one thing that I failed to put in there, guys. I failed to put in dx's, which is going to be a bit of a pain. So let's go up here and let's go ahead and add in our dx's. So we're going to say dx. And this is going to be a float 64. And we're going to yank and paste that twice for dy and dz. Okay, let's go ahead and dd here. And what do I want here? I guess what I'm going to do here is read in a dx, a dy, and a dz. This is getting complicated really quickly. Let's pop here. And let's bring this down to the next line. Why not? dx, dy, and dz. Float 64. And I'm sure there's going to be something that's going to pop up when we compile this. So let's do 64. Okay. So we have the float 64s. Let's pop here and let's just read in dx, dy, and dz. And in some sense, maybe I don't need a full initialization function for this, but it's fine. It's fine. Okay, so we're gonna do. Let's just fine. We're gonna have to read in dx's. No, the dx is already here. Oh no, they're not because we haven't initialized it. Dang it. It's good for what it is for. User base. Only downside is package void Linux. I see. When I can choose, I prefer BSD over Linux on servers. That was also a thing for FreeBSD ditch over Arch. Arch wasn't scalable for tasks compare like Red Hat Linux BSD family. I'm not sure. Actually, I'm curious to see what tasks those are. You know what I mean? Like, I'm not actually familiar with the differences. 1 second. And let's pop down here. So I'm going to bring this down to the next line. Oh, this is getting super messy super quick, but that's okay. My bad, guys. We can clean it up in a bit. I always say that, and I never do. Okay, let's pop over here. Let's do int64. And put that here, too. Okay, int64 here, and let's do dx and dy, and then 0. Okay, good. So we have everything set. And what are we going to do here? Well, we have the dx's. We have the index. So we have the i's and the j's. I think everything's good to go. So if we have a dx, basically all we need to do is we need to say, let me think. If we have j, man, counting at 1 is weird. 1 second, I have to think here. Okay, but this should be okay. Let's just pop down here and let's go from there. So we're going to say square root. So first let's find the position of each individual point. So let's go down and let's do that. So we're going to say position. Yeah, so we're going to say position. Let's see, vortex. Oh, point, I suppose? It's going to be equal to position of, I guess we're just going to give it an XY position, right? So we'll say I plus 1, because we're always going to be off by 1, because Julia, times dx. Okay, and then it's going to be j times dy, and then 0. Okay, and what I'm going to do is I'm actually going to put this distance function in a separate function up here. So let's go down and let's say function to find distance between two positions. Okay, so it's going to be function distance, and this is going to be of x1, I suppose. I guess position. That's super ambiguous. Let's not do it that way. Let's say, I guess x1. No, but x is location. Fine, location. Here we are. And then we're going to go down here and we're going to say, oh, position. Location 2 of position. Oh my gosh, what am I doing with my life? And Here we are. RO. Okay, so here we have that function distance. And we're just going to return square root of the following. So it's going to be position 1, position 2, dot x, dot y, dot z. That's all it has to be. So it's going to be position, so let's do location 1, dot x, times location 1, dot x. Oh, x squared plus y squared plus z squared. So let's just go up here and let's define x is going to be equal to, and what do we want here? I suppose we want location 1, x minus location 2 dot x. And we're going to change this to a y. There, and of course there. And then change the next one to a z. Let's do there. Okay. So now we just say the following. We're going to say return square root of x times x plus y times y plus z times z. And because, of course, these guys are all squared in the end, it doesn't matter which one we subtract from the other one. It should be okay. So as long as we've initialized this position correctly, then we have the location of everything. We should just be able to find a distance. So we're going to say, what do I have here? Distance is that. Now, let's see. How do we find the angle between two different points? I suppose this is just going to be rise over run. No, the angle is going to be, we have the distance. Okay, so it's going to be the distance between the two. We have the two different points. Yeah, okay, so we can just take the tangent of the two x's. Yeah, this will be fine. This will be good. This is good. This is good. So now we're going to say radius is going to be equal to distance of position, point, and what's the other guy we want here? We want point and location of k. Okay, so now we have to find the other one, which is going to be a function. Function, 1 second. Linux is written by hobby students. Is that true? Because, like, I thought, so I know Linus initially made it as a, let me see. My only interaction with BSD now is C functions that originally came from that ecosystem. Yeah, I honestly don't see BSD that much, but I guess I don't really know the difference between BSD systems and Linux systems. So I'm not really sure, you know, again, what the difference is. So function to find the angle between two positions. Okay, so this is where things get a little bit funky. So because we're going to end up having two different angles, a phi and a theta, we have to think about how we want to do this one exactly. Okay, so what we'll do here is we're going to say function find, I suppose we want, there's going to be two different angles, right? So there's going to be one that's around xy. Let's go ahead and draw this out on the other screen. So page, new page before. We're going to need two different angles here. We're going to have one angle. Let's see. That goes, oh, that wasn't what I meant to draw. Let's draw it like this. Okay, so we need one angle. Oh gosh, this is awful. That is drawn here. And then another angle that is drawn here. Okay, so we have one angle going this way and another angle going this way. Let me see. Arch is awesome at creating personal system, which makes every system a bit different for the whole beginning. When you are going to deploy several machines and maintain it with the rolling updates, etc., it gets a little over your head compared to LTS release. But if it's your personal computer, you're using it and maintaining it at least weekly. Let's see. If 386 BSD had been available when I started Linux, Linux would probably never have happened. Yeah, fair enough, right? I mean, I don't know. We'll see. Okay. So let's just go ahead for now. Assume that we're in the XY case and just find the angle between the X's and Y's, and that should be okay. I think that should be fine. I was talking about personal use as well. Yeah, so I'm actually not sure. So let's say find, what should we call it? How about we say angle XY? That's an awful name, but that's okay. Location 1, position. Location 2, position. Okay. So let's go ahead and end this one. Pop down here. And we're going to say return. And I suppose, let's see. tangent is equal to opposite over adjacent, right? So let's go ahead and find the x's and y's. We're going to say x is going to be equal to location 1 second, yank to yank, paste, and now we're going to say return. So tangent is equal to opposite over adjacent, right? So if tangent is equal to opposite over adjacent, and we're looking for theta, then it's going to be arctangent of opposite, which is going to be y over x, and that should be it. I was talking about personal use as well. I don't think new BSD would be any more popular than new Linux is now. I don't know. I mean, new Linux is super popular from my perspective. Ghost BSD is nice BSD if you want to get a taste of it. But yeah, I suppose if Linux was replaced by BSD, maybe that's true. I mean, in the end, Linux is popular by necessity, right? And again, I don't know. What I don't know is whether the genetic. You finished the genetic algorithm? Let's stop for now. So with the genetic algorithm, we have something that is optimizing. There is a little bit of debate whether it's truly a genetic algorithm. That's fine. But for now, what we're doing is we're writing up a quick superfluid case because I want to use another genetic algorithm to do some cool superfluid stuff. And that's kind of what we're at now. So we're going to come back to the genetic algorithm in just a bit. But for now, I wanted to kind of take some time and code up this superfluid field finder. And that's kind of what I wanted to do here. So we're going to do function find field 2D. And in the end, we're going to have to return the field. So in the end, we're going to do return velocity. Okay, so now we have the radius. Let's go ahead and also find the angle here. So let's say theta is going to be equal to angle xy between the two different locations. So we're going to say point, and we're going to say location of k. Okay, so this allows us to do multiple vortices, although we'll only start with one. There's no debate anymore with the thing we talked about in Discord. Yeah, okay, that's fair enough. But you're right, it could have been better written, and that's fine. Okay, so angle xy, point. Okay, so this is everything we need. We have the point, we have the radius, everything's good here. And if we assume that we have the same amount of, I suppose, circulation around every vortex, we can go ahead and find the field at every point. So let's do it. So now what we're going to say is the following. Open, go down here, and we're going to say velocity dot x is going to be equal to, what do I want here? Velocity dot x, how are we going to do this? This is going to be equal to, okay, so we need the cosine of theta attached to what we typically have. So this should be, unless I'm doing something really, really stupid here, it should be the radius. Oh, wait a minute. To change from theta to, it should just be cosine theta to change from theta to x, right? So I guess it's going to be this. Let's try this out. So I'm going to assume the circulation is just 1. Don't kill me here. And then we're going to do 2. Pi is natural, right? Yeah. 2 pi. Oh, actually, Julia is quite neat. Look at this. 2 pi. You ready for this? Bam! 6.28. We didn't even have to put a multiplication sign. Automatically. 2 pi. It knew it. Sorry. You can also use Japanese symbols if you want. So if I wanted to do, I don't know, we can actually use any language symbols for Julia too. So let's just do 2 pi, and then we're going to multiply this by the radius. And then this whole guy is going to be multiplied by cosine of theta. So let's do cosine of theta. And that should be fine for x. Now for y, we're going to do our y. Pop down here, and this could be sine of theta. Let me see. I feel like I did something wrong with the unit conversion here. Let me just very quickly pull out a book. This is why I hate doing this at 5 in the morning. My brain's never quite right. So let me see. I'm looking at Griffith's Electrodynamics, by the way. At the very front of Griffith's Electrodynamics, there is a page that has unit conversions. Let me see. Maybe it's on the back then? Let me see. Oh, it's in the back. Sorry about that. But this is to spherical coordinates, cylindrical coordinates. Let's see. S cosine of theta, theta, tangent negative 1. Yep, this is fair. Okay, so if I want to go from theta to x and y, x is equal to s cosine theta. Yes, okay. That's fair enough. I need a radius. We should write a Julia program with emojis only. I think it's totally possible. But unfortunately, my terminal will not depict emoticons. So that's something I need to kind of put in. Okay, so we have velocity x. The one thing I don't like about this is that the x... Yeah, this should be okay, right? So we have some sort of... This should be right. Maybe it's wrong. Maybe I have to multiply it by another radius, but that doesn't make any sense. This has to be right. So if it's... Yeah, this is right. This is right. This is good. Okay, so now we have the velocity x, the velocity y. These are all found. So we have the find field 2D. This is all good. So now let's just go ahead and create a very quick main function, and let's go from there. So how do we do this? We're going to say function to find field... main function, whatever. So we're going to do function main. I don't know what I'm doing anymore, guys. I'm sorry. Your channel should totally show Unicode symbols. Oh, yeah, Unicode symbols. You're right. Let's pop down here. Now, what do we need for main? I suppose a couple different things. Let's go in here and let's read in xdim. Oh, Nah, this is fine. We'll just define everything in main. So let's go ahead and define all the things we need. For now, we're just going to set xdim, ydim, and zdim to 16. So we're going to say xdim is going to be equal to 16. And then we're going to do the same for ydim. And then for zdim, we're going to do something super special here, guys. Zdim is going to equal 0. That was an x. Okay, so now for the dx's. I suppose for the dx's, yeah, you guys are right. I'm sorry, I wasn't thinking. I actually don't know how to type Unicode symbols, so that's something I need to kind of figure out, but that's okay. Okay, so we do zdim equals 0. So now what are we going to do? We need to go ahead and define a vortex location. So we have the positions. Let's just go ahead and create a vector of positions. That's what we need to do. So we're going to say vortices is going to be equal to vector. How about we do fill? No, fill doesn't make any sense in this case. I suppose what we need to do, how do we go ahead and assign this? So we want vortices to be a vector of vortex, or a vector of positions. Okay, that's what we want. Okay, so if we say vortices, this is going to be equal to a vector of positions. So I suppose we need... I guess we could fill it to start? Yeah, I'm actually not sure how to do this one. Location vector. Let's do, we only want one of them right now. So what if we just do something like this? And we say position. And let's just put it at 0, 0, 0 or something like this. Is that okay? Let me think. Yeah, this should be fine. We'll just put it at 0, 0, 0. So we'll do 0, 0, 0. I don't know if this will actually work or not. So let's go up here to the top. Let's put the position type into here. Okay. And then let's check that out. I think it should be okay. But we'll see. Oh, space before and allowed in vortices. Oh, I think I need an equal sign. There we go. Totally forgot an equal sign. There we go. Got it. So now we have the vortices. Now what we have to do, I think, is just read this in. So let's see what happens. Xdim. I suppose we should do a dx. And I'm thinking I want to change how we're doing this xdim, ydim, and zdim. We have all the dimensions. Let me see. This will be okay. It's okay for now. So let's just go ahead and do xdim, ydim, and zdim, and they're all the same. If you're using Japanese IME, it shows emojis when you type something. At least it does mobile. For example, when I type, it automatically shows up. Oh. Interesting. So I might try that in a bit. So let's say now we want dx. And this is going to be equal to, let's do 0.1 or something for now. It doesn't really matter for now. So we're going to do ry and rz, and this is going to be equal to 0. Okay. So just to make sure we have everything, the vortices are all set. So now let's go ahead and do find field. What do we want here? 2D. And we're going to read in the vortices. And then what do we want? We want xdim, ydim, dx, and dy. And that should be that. So let's go ahead and write this. And let's just run it in Julia just to make sure it runs. Let me do a quick pwd. Oops. Control D. pwd. I'm in the right directory. Now let's type in Julia. How do I run other terminal commands in Julia? I don't actually know. Sorry about that. Let's do write this. Let's go over here and let's see if it compiles. Let's include. What do we want here? I suppose a Superfluid. I called it Vortex. Vortex.jl. And it breaks on line 32. Let's see, what do I do here? Function init field. What is the issue here? While loading, starting at line 32. Function argument names not unique. Okay. Function arguments names not unique. What is it? xdim, ydim, xdim. Oh. My bad. Include 57. Bam, down here, find field 2D. What's the issue here? An expression starting line, event, float. Okay, misspelled float. Knew that one was coming. I always misspell float. So I like doubles. Main. Warning, method definition. In64, in64. In module main. Overwritten. Vortex.jl. Let me see. Method definition. Type main.position. 1 second. What is all this? Warning, method definition. What is this? Module main. Let's just go to 51. Okay. X equals location.x, location2.x. Let me see. Method definition. Type main.field. In64, in64. One thing Python really banged in my head was good naming of everything. Often you can tell if a scientist mathematics code by shortening is when they shorten. Yeah, but in this case, I don't typically do that. I do my best not to. Again, we have x, y, and z, xdim, ydim, and zdim, and dx, dy, and dz. But these are all, I do my best not to, you know? Because I hate when I have to go through a code, and I have to find something like an L, or something like that. Like one of my angular momentum in physics is typically notated as an L, which is a big pain. If you have a lowercase l as a variable name, and you have to find all of these lowercase l's, I don't know, it's a pain. So I usually do my best. But of course I'm not great at naming, but I think it's okay. Okay. So let's do this. Method definition, array float in module main at Superfluid Vortex 9, overwritten at, wait, what? In module main at 9. Okay, xdim, type field. I've converted a program that has variable names of half alphabet. Yeah, it is kind of a pain. But again, there are some things that I do kind of take for granted, and I will totally admit this. In certain cases, it just makes more sense to use mathematical notation. You know, because if you have a choice to write circulation versus gamma, and everyone knows the formula because you've written the formula in a comment, this is fine, you know? That's not a big deal. As long as somewhere in the code you've defined all the parameters so it's readable, I think that's okay too. Okay, what are we saying here? Another one, warning at line 9. They're all overwritten at line 9. 26, int 64. Man, what does this mean? Method definition, init field. What does it mean, method definition overwritten? Let me just go over here and say method definition overwritten. Method definition error. Let's see if we can figure this out. It's overwriting methods. Let me see. Well, what did we do here? Error x, methods t. Let me see. Method t. Definition. 1 second. Methods t. 3-element array. Method definition. Type module main. Overwritten. Wait, what? I'm a little bit confused as to what's happening here. Let's pop over here. I mean, I guess it should be okay. Let's just go ahead and run it. I guess it did run, didn't it? So let's run main. Float error. No method init field. Int 64. Float. Int 64. Let me see. Init field. Where's init field? Should be no matching init field. Int 64. Int 64. This should exactly be what I have. A float 64. Oh, wait, what? G? Oh, I see, because it's 0.0. Main. No method matching. Oh, I forgot to re-include it. Main. What do we have here? No method matching init field. What? Vortices position 000. Vortices axiom. Oh, okay, so it's up here. I see the problem. This is not a 0.0. Let's go ahead and do this 0.0, and this 0.0 up here. We have to re-include it. Main. Okay, what do we have here? Candidates are method error, no method matching in 64 float 64. Where's the float 64 coming from? Oh, dagnabbit, that's my fault too. There we go. Now let's re-include it. Let's try main. Now what the issue is. Field not defined. 1 second, let me see. Find field 2D. At home. Vortex 97. 67. I guess we just go to 61. Here, XDM field. Wait, what? Field, not defined. Field. Okay, so I guess in find field or init field, I called it lowercase field. Yep, that's what I did. Pop down here, change it to lowercase f or uppercase F, RF. Include again, main. And let's see, what do we have here? Init error, find field 2D, inexact error. Okay, find field 2D, array position 1, fair enough. I think we already had a Discord command. But yeah, guys, if you are available and you want to, feel free to stop by the Discord server we have for the Twitch programming stuff. And it's actually quite fun. Let's see, what do we have here? So yeah, the Discord server is over here. I'll check it later. But yeah, so feel free to check there if you haven't already. Okay. So what do I want to do then? If we can just get this guy to compile, I'll be happy for the day, and then we can kind of test it tomorrow. I've got a feeling there's going to be some sort of weird physical bug we're going to run into, but let's just make sure it runs, and then we can worry about. We could probably plot it today too. Let's do the plotting. Oh crap! I got to be gone at 7. That's okay. That's okay. We got this. We got this. Okay. Let's go down. What does the inexact error mean exactly? So we have in64, array position, in64, float 64 at 73. In main at 97. So I guess it's 73. Let's pop here. Here, point equals position. And position should be doubles, right? So I guess what we need to do here is my mom totally goes. I regret having you come with me. Oh, I'm sorry. So what do we do here? I guess we need to call these guys doubles, right? So how do we cast onto a double in Julia? Cast onto float 64. Julia. And let's see what do we have here. Conversion and promotion. So type of... All I want to do is... But let's do it over here. So let's say A equals 1. And let's say double or float 64 1. Okay, good. So I guess we just do float 64. Let's do that. Float 64. Here. There. And let's do float 64 over here. And there. Let's try this. Include. 1 second. Include. Main. Inexact error. Still an inexact error. Let me see. There seems to be some problem with the old Discord link. Oh, interesting. The command Discord has been edited successfully. Okay, well now you guys should have access to that link. Sorry about that. Also, Edge, I'm sorry. I recommended a more expensive model because it will be better for a back. It's also a couple K more. Ooh, it's quite expensive. But yeah, good luck with that one. DX, what do you have here for DX? DX is going to be, they're going to be floats, so that should be okay. Let's go to position real quick. Position is here. Oh, I see. I defined these as X, Y, and Z, but these need to be floats. So let's do float here. Pop it there, and pop it there, and remove a T because I accidentally had an extra T. And let's see, what do we have here for positions? Where else do we define position? We have position, vector positions there, but that should be okay. Let's pop down here. Vortices position 0, 0, 0. So I guess it should automatically cast that, right? Redefinition of constant position. What do we have here? Oh, I guess just Control D, Julia, include, main, pop. Okay, so can it convert? Object type float 64. I saw this one coming. Oh, I have a large sway on her purchase because of how I think. She agreed and she is buying that one tomorrow. Well, good luck. I know my mother also has back issues, and actually my entire family has some sort of back issue. Not entire family, but like I've got back issues too, but I don't know why. So this is kind of why I use a standing desk and stuff like that. Okay, what do? I want to do arisen from constructor float 64, find field 2D. Let me see. That's going to be in line 76. Velocity.x is going to be equal to the following. And what's the error? Cannot convert an object type float 64 to an object type array float 64. This is my fault. This needs to be x, and what we need is index here. Oops. There we go. And we need another index here. There we go. Now let's see what happens if we run include. We do main. Okay, what's the issue here? It says line 76. So it seems like we still have an issue. What is the issue here? Main at home James projects Simuleo Superfluid Vortex 97. Okay, this is there. It's still 76. Attempt to access 0 element array float 64 at index 1. It's got a double engine mechanical recline, so you can sort of adjust how it presses on your back. Interesting. So what do we do here? Find field 2D. Vortex 76. Array position 1. Attempt to access 0 element array. Let me try something. Fill. We're just going to do 0.0, and we're going to do 10. And we're going to set A equal to this. Now we're going to grab A of 5. That's equal to 0.0. Okay, so no problem here. So velocity x when we init field, for some reason it's not being initialized correctly. So let's go up to init field. And what do we have here? We have empty array field of G size, and it says it's a 0 element array? No way. No way. Let me go up here when we are initializing the field. Now let's print something out. Let's go print line, empty array, and let's just do 10. Let's go here. Let's do include. Let's do main. Attempt error, access 0 at 36. Yeah, okay. So the empty array is not working the way I anticipated it working, which is a little bit weird to me. Fill 0.0 G size, that should be okay. G size should be X dim times Y dim times Z dim. So I guess we'll also print out that. Let's do print line. Oh, I guess I should leave that line in there. And let's go ahead and print line over here. Oh my gosh, I see the problem. ZDIM is 0. That's totally the problem. Let's go down. Where do we init field? In this case, this can't be a 1. This has to, or this has to be a 1. R1. And that should probably do it. ZDIM is going to be equal to 1. Let's pop down here. And let's do include. Let's do main. Okay, so now it kind of sort of works. Okay, so we have a field, and we have everything set. So now I think we have it running. So let's do velocity. It's going to be equal to the following. Find field there. Okay, so now we have everything working, and I suppose just super quickly we can do a plot. I don't see any reason why we can't. We'll just see what happens. So we have a .x and we have a .z. Oh gosh, no, we don't quite have that, do we? So we have a whole bunch of points, but it's in a one-dimensional array. So what we need to do is we need to reshape this array before plotting. That's what we need to do. So what do we do for the reshaping? I suppose we can write a separate plot function that plots 2D, and that would work okay. Let me see, how do we do a 2D plot in PyPlot? Not really quite sure. So let's just go over here and let's do using PyPlot. Just because we've used PyPlot before, it works relatively straightforwardly. So let me do the following. We're going to do, you know, I could just reshape it, output it, and put it into NewPlot. I know how NewPlot works. I like NewPlot. Anyway, let's go. So we're just going to do plot. And let's do 1. Okay, plot's the 1. Let's do plot 1, 2, 3. Okay, so that didn't seem to work. Here's what I'm going to do. I'm just going to go ahead and we're going to do an output function. So let's do the following. We're going to create a function up here, and we're going to say function to output data in a new plot fashion. Okay, so here we're going to say function. Oh my gosh, what am I doing? Function output. Let's do output 2D. And this should be okay. And what we're going to read in is a, let's say, field velocity, which is a field. Something like this. And here. Okay, so we have to do a couple of different things, but it's not going to be so bad. So let's pop it out. Let's see. So we have X, Y, and Z. That's what we need to do. Yeah, so we can actually plot this in a number of different ways. So let's go ahead and let's do the following. So how do we write a line in Julia? So we're going to open up a file name. So we need this, and we also need string file name. Is there such a thing as a string in Julia? Okay, so it seems like there is. So let's do the following. We're going to say file name string. Okay. So we have the file name. So let's go ahead and open up the file. So we're going to say open file name. And it's going to be just right, so I think we're just going to do W here, except lowercase w. And in the end, we're going to have to close it, so let's do close file name, and that should be okay. Okay, so we have it open and closed. Now, how do we write to a file? Let me think. Writing line by line to a file, Julia. Julia. Introducing Julia working text files, writing to files. We'll get this function written, and then we'll test it later. So let's see, there should be a write function here. Control F, write. Let's see, write F, ABC. That seems okay. But I want basically print line, but I want write line. That's what I was hoping for. But if we don't have that, that's okay. We'll just do something like this, and that should be okay. Let me see, what do we have here? N1 open temp. Let's see, I20, N1 equals 4 random numbers. Yeah, that should be okay then. We'll see what happens there. So we have this. Let's just kind of go through everything. Let's go here and say opening files. And let's see, what do we want here? I guess we want file name plus X. And close file name plus X. Am I allowed to do this? I have no idea. No earthly idea whatever. Whatsoever. So let's go ahead and do ry, paste, and ry. So we're opening up two files, and now let's go through and let's say 4. Let's say I equals 0 to x dimension minus 1. Is this right? Yeah, that should be right. Now we're going to do y to y dimension here. We're going to have to put in 2 end statements. So let's do an end here. And of course an end here. Okay, so now up here we have an index. And we're going to say index is going to be equal to exactly what it was before, which is j plus I times y dimension. There we go. So now we have our index. Good. So now we have all that set. Now all we have to do is basically output the data to each individual file. So let's go ahead and do that. So we will do, I suppose, the following. And it will be write to the file name 1 and file name 2. So let's see, what do? We do open. I suppose we say file equals open. So let's go up here and let's say X file and Y file. And let's pop down here and let's say Y file. And let's go down here and let's say close X file and Y file. I think that's actually how the syntax works. So let's do X file. And let's go down here and let's do Y file. Okay, so we're almost done today, guys. Sorry about that. X file. And then what are we going to write? We're going to write the following. So we're going to have to write IJ. No, so we're going to have to write X and Y. So let's pop up here and let's go ahead and find those guys. And let's see, what do we have? Oh, it's right there. Distance point. Yeah, so let's go ahead and find, let's find those guys. So we're going to say X is going to be equal to, what do we want here? Float 64 this. And then we're going to go down here and we're going to say Y. It's going to be equal to float 64 j times dy. Promise we're almost done, guys. Sorry about that. So let's pop down here, and we're going to write down, I think it's just going to be $x. And then we want a tab. Then we want $y. Then we want a tab. And since this is the x file, we're going to want $velocity.x of index. And maybe this will work. I have no idea. We're going to have to do the same for y file, yank paste. So let's do y file, ry, and ry. Let's pop down here to main, and let's just do output 2D. So it's going to be output 2D, and we want to read in velocity. And file name, which I'm just going to say is out. So let's pop over here and let's do, what is it? Include vortex. And let's see, what do we have here? Ydim after end of expression. So let's see, what do we have here? These are not xdim and ydim, they will be velocity dot. And velocity dot. Try it again. Let me see, what do we have here? Ydim after extra, wait, what? 1 second. Extra token ydim after end of expression. User input 94. I times. Include 86. Function output 2D. Let's see, what do we have here? 64. No, 89. X file. Let me see. Invalid type for argument file name in method description. Okay, so let me think here. I suppose we need to do file name X and file name Y, I suppose. So let me see. That's what they do, right? Open. Yeah, so they do that. So let's go here and let's say file name X. It's going to be equal to file name plus X. Should be okay, I think. So let's say X equals hey. And then we say X plus H. Oh, what? You can't add strings like this? Crap, how do you add strings? Is it cat? Add strings, Julia. I guess it's maybe cat or something like this. Characters, X type of adding. Nope. Additional, in addition, int, added. All I want to do is add strings together. Okay, so I guess we just use string here. So it's gonna be string, and it's gonna be good to go from there. Here, there, here, and there. Going to include vortex.jl, and let's see, what do we have here? Output 2D, vortex 89, macro expansion, inline, 89. It still says 89, right? 89, really? Okay, what's the issue here? Argument error, invalid type for argument file name and method defining output 2D. Let me see. Oh, I see. I need a comma. My bad. Let's try this. Wait, are you kidding me? 1 second. I have to think here. File name method, invalid type. What? Okay. Let's say X equals string of hey, comma. Okay, that one works. Why does this one not work? File name is a string. So let's say X is equal to string of X and comma. Okay, not exactly sure. However, it is currently kind of late in the morning for me, and I do kind of have to get going. So let me see. Argument error, invalid type, argument file name in method definition for output 2D. Let me see. Superfluid vortex 89. Invalid type for argument file name. Invalid type for argument file name. What? String. Macro expansion while loading an expression 86. Yeah, so 86 should be this one. Yeah, so that's the function 2D. Output 2D. Well, I'm not exactly sure what the issue is here. So string Invalid type for argument file name and method definition for output 2D. What? This should be totally right. What if we just do X and Y? X.dat and Y.dat. Screw it. There. Include. Let me see. Invalid type for argument file name and method. I'm not even using file name. One second. Let's remove file name entirely from this. Let's pop down here. Remove this entirely. Include vortex. Oh, why did that one work? Where's main? J not defined. Okay. 1 second, guys. Gotta fix that. Pop over here and let's do include. Main. Let me see. YDIM not defined. That's fair enough. This is velocity.ydim. Include. Main. DX not defined. Of course, this is again another issue. This is velocity. And this guy is also going to give me a bug. Here. Let's do include. Main. Okay, this one seems to run. Let's do a control D. Let's see what we have here. VI, ls real quick. We should have an x.dat, y.dat, vi x.dat. Okay, so it looks like we, dag nabbit. It's not what I wanted. Yes, that's not what I wanted at all. Okay. Well, that's not what I wanted. Xdim, ydim, and, okay. So what is the issue here? It gave me a full field. I just wanted one value. So maybe if I do this. Let's pop up over here, right and quit. Let's run Julia. And we want vortex.jl. Now it's vix.dat. Okay, it's doing the same thing. Let's remove x.dat. 1 second. Julia vortex.dat, vix.dat. Are you not outputting anything? Why are you not outputting anything? What? Julia? One second, so we're going to do the last include. Bound error, except attempt to access 256 element flow 64 at index 0. Why didn't you give me this before? 97? Velocity x at index 0. Index is equal to j plus I times... Oh, I guess we have to start at 1. Include. Okay, so now let's go into control D, vi x.dat. Okay, so one thing I totally forgot to do is print a new line at the end here. Okay, so now let's go ahead and run Julia vortex.dat, vix.dat. Okay, so this seems to be okay, I think. 2, 3, 4. Let me just run new plot. 1 second. Control D. Oh, come on. There we are. We're in new plot. Now let's plot. Splot, sorry about that. X.dat. And let's see what happens. Okay, so this actually doesn't look so bad. It might be what we expect. Not really sure about that. So this is something we'll have to look into next time. But we do see, let's do a quick set. PM3D. Now let's plot it again. Oh, that didn't help. But that's okay. So basically, guys, we have something that's increasing around 0, 0, which is expected. We got a little bit of stuff we have to kind of think about real quick. And we will see basically what happens here. But anyway, guys, that's it for now. Let me go ahead and close here. Let me do a quick right and quit. And let's do git add vortex.jl. Git commit. Adding simple vortex field finder. And let's do git push. origin master. Okay, so that's it for the day, guys. We have our simple Superfluid stuff working. In a way, we got to test it just to make sure it's actually working the way we want. And then after that point, we can go and work on the genetic algorithms one more time after this. So tomorrow, basically the idea is we're going to test this, make sure it's actually working the way we want, put in multiple vortices, see what happens, you know, that kind of stuff. And then we're going to go back to the genetic algorithm stuff where I have an idea to find these fluids or to kind of make a vortex finder type of thing. It's going to be super fun. I'm actually really excited for this because it's an active area of research and quite useful. Anyway, guys, thank you so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos. Also, feel free to check out that Discord link that Gusfern just posted in the chat. Should be super fun. We actually have some pretty good discussions going on there throughout the day. And I'm quite happy that we have that community now. It's very useful. Anyway, guys, I will see you around. Thanks again. Have a great time, whatever time it happens to be. And I'll see you next time. Bye, guys.